Hello everyone. My project is called AI powered X-ray visualization and damage detection for pneumonia. Pneumonia is a serious lung infection that affects millions of people every year. Early detection is very important because delayed diagnosis can lead to severe complications. Normally, doctors analyze chest X-ray image manually, which requires expertise and can take time, especially when hospitals handle a large number of patients. The objective of my project is to build an AI system that can automatically detect pneumonia from chest X-rays images and explain why the model made that prediction. The main motivation behind the project is that many AI models give predictions but they behave like a black box. In healthcare, this is a major problem because doctors need to understand the reasoning behind a prediction. So, my system focuses on two main goals: accurate pneumonia detection using deep learning, explainable AI visualization to highlight infected lung regions. For the training model, I used chest X-ray pneumonia data set from Kaggle, which contains thousands of labeled X-ray images. And the data set has two categories: normal, pneumonia. Before training, the model I implemented a data pre-processing pipeline. The pre-processing steps include resizing all images to a fixed resolution suitable for neural networks and normalizing pixel values to improve model stability, applying data augmentation techniques such as flipping, rotation, and color adjustments. Data augmentation is most important because it helps the model learn different variants and prevents overfitting. Finally, the dataset is divided into training, validation, and test sets. Wait, I will show that the datasets. Yeah, dataset divided into three types: test, train, and test set validation. You can see normal all dataset images, pneumonia images. The deep learning model used in the project is DenseNet 121. DenseNet is a convolutional neural network where each layer is connected to every other layer. This architecture improves features, reuse and reduce the number of parameters compared to traditional CNNs. Instead of training the network from scratch, I used transfer learning with pre-trained ImageNet weights. This approach helps me in two ways. It reduces training time, it improves performance, and when the data is limited. I modified the classifier layer to match the pneumonia classification task. The final classifier structure is 1024 neurons to 512 neurons to 2 output neurons. The output neurons represent two classes, normal and pneumonia. The training pipeline is implemented using PyTorch. The optimizer used in is Adam, which adapts the learning rate automatically during training. I also used a learning rate scheduler called Reduce LR1 Plateau. This scheduler reduces the learning rate when the validation accuracy stops improving. During training, the model performs the following steps: forward pass to generate predictions, loss calculation using cross entropy loss, back propagation to update weights. The system tracks both training accuracy and validation accuracy. This is the most important part of our project. One key feature of the system is explainable AI using Grad-CAM. Grad-CAM stands for Gradient Weighted Class Activation Mapping. Normally, deep learning models act as black boxes. Grad-CAM solves this by highlighting the region in the X-ray image that influenced the model's prediction. The process workflow as gradients from the final convolution layer are calculated. These gradients identify which regions contribute most to the prediction. A heat map is generated and overlaid on the original X-ray. The heat map uses colors to represent intensity. Green indicates low impact while red indicates high impact. This helps doctor visually see which lung areas are affected. To improve visualization, I also created a 3D lung representation using Plotly. The Grad-CAM heat map is mapped onto a parametric 3D lung surface. This also users to rotate the model, zoom into affected regions and analyze damage intensity. This interactive visualization makes the results easier to interpret. To make the system user friendly, I built a web application using Streamlight. This is the application I have built. This application allows users to upload a chest X-ray image, get a real-time prediction, view Grad-CAM visualization, see the 3D lung model, and download the medical report. This inference time is around 2 to 3 seconds on CPU, making it suitable for real-time screening. Yeah, now I will test an image. Okay. Yeah, it's showing normal, 99%. It's generating Grad-CAM visualization. Wait. Yeah. Severity normal, and these are the severity levels, and this is our 3D lung model. In this there is no pneumonia presented, so it looks like some low contrast images. Yeah, here we show severe damage, moderate damage, mild damage and health issue. So there is no issue in this in these lungs. Yeah, here is a medical report we can generate by our application. Okay, I will test with another image, like with pneumonia image. Yeah, it should say pneumonia detected for these lung images. Yeah, here you can see severity is 100%. The here is that where the lung affected is shown by this 3D model. Yeah, you can zoom into and we can rotate this model, so we can see clearly where the lung is damaged. Yeah, this is recommendations by our web application, and here the report generated by our application. This is our web application. This is how the how our project is worked. This model achieves the following performance metrics: accuracy around 92%, precision around 91%, recall around 94%, and F1 score around 92%. No AI system is perfect. Some limitations of this project include: the model is trained only on a cargill dataset. It is not yet support real hospital DCOM data. Clinical validation is still required. Future improvements could include multi-disease detection, ensemble deep learning models, and integration with hospital systems. In conclusion, this project demonstrates how deep learning and explainable AI can assist doctors in pneumonia detection. The system provides accurate predictions, visual explanations, and interactive web interface. However, it is designed for support and screening purpose only, not a replacement for medical professionals. Yeah, thank you. This is about our project, and now I can show the results. Yeah, this is models. This is our training history, training and validation loss. Yeah, yeah, that's it. Thank you.